investigation on how the PID control loop algorithm influences the optimal deceleration of X robots. The research question is, to what extent can the PID coefficients be unified for different types of XIQ two-motor drivetrain robots programmed with the PID control loop algorithm? But first, an introduction. When working with robots, programmers always think about how to make the movement more smooth, accurate, and efficient. A way of doing this is through control loops, which help to deal with scenarios where robots have to get from point A to point B with a limited time frame and to not make any sudden movements so that the object they're carrying isn't dropped. Control loops are used all throughout industry, and you see this both in factories or even in the automotive industry as well. The PID, proportional integral derivative loop, allows for both better braking control and turning stability, and is commonly used among all sectors of industry. Using these three components allows programmers to reach smooth acceleration and deceleration. The aim of this essay, or investigation, to be more accurate, is to first understand the PID control loop algorithm. Then, it's to find the optimal coefficients P, I, and D for two-motor Vex robots, as they do not currently have a well-developed integrated PID system, and hence achieve optimal acceleration and deceleration regardless of robot weight or the distance traveled. So, let's get into some background knowledge, shall we? The PID loop is an algorithm commonly used in industrial systems and autonomous systems. It indefinitely calculates the error between the desired value, the distance from origin to the destination, and the curve value, which is the distance to destination. In a sense, the error is a sort of difference which helps us get the proportionate value later on. It applies a correction in the form of three components, which I already mentioned, P, I, and D, standing for proportional, integral, and derivative. Examples include assisting vehicles to ascend up slopes and maximize out power and distance traveled as well. Another example is arms or claws gripping objects with force matching the weight of the object so as to not crush the object or to drop it. In these cases, PID would slowly decelerate the vehicle per arm as distance to destination decreases, making it stop right before the destination. First, the proportional component. This is by far the most important component. There exist loops without I or D, but never without P. There are P loops, there are PI loops, PD loops, PID loops. Never are there loops with just I or D. Never. This is because the others cannot detect the present state of the system. And as a result, the P component, proportional, is, well, it can be considered very simply as the present component. It's calculated by, the output power from the P component is calculated by first getting the average position of the robot at that moment in time, by getting the position of the left motor and the right motor, and taking an average. Then you find the error by taking the set point, which is the destination / target, and again, I'm using the average position found here. Finally, you multiply error, which is found here, and TP, the proportional coefficient, which will come into play later, to get the power, which comes from the proportional component. Then the D component. Now I know the algorithm is PID and all, but there is a reason for why D comes first when it comes to tuning. Opposite to the I component, the derivative component calculates the rate of change in distance and checks whether slowing down is necessary. It can be considered, in a sense, as the future component. It's normally not as large in magnitude as the other two components, but it will build up noticeably faster than even the I component during integral winding. And believe me, that is fast. Why is this useful? This is useful because it slows down the robot's speed when the rate of change is too fast, and also vice versa. Another advantage is that it has very little detrimental effect on the output, making it more useful than the integral component for most purposes, but not all purposes. How's the derivative component calculated? First, you take the difference between error and previous error, which is the error a set amount of time ago. So let's say that it's 20 milliseconds in the case of a classic robot. Then you assign the meaning of error back to previous error, and finally you pick up and you find the power which you found from error times kp in the proportional component, and then you use the derivative which you found here, and you multiply it by the coefficient that can be used by the user, PID. And finally, you found that you multiply those, add these, and find the output power. Finally, the integral component. This is the component that takes into consideration all of the distance covered beforehand. And at some point, the proportional component will stop inputting power due to the target being too close, which is where the I component will give a slight push in power to eliminate that one small bit of error that's keeping the robot back from actually reaching the destination. However, it has some very serious detractions. One of them is that it's very susceptible to overshooting the target entirely, as it doesn't reset that easily. Another thing is that it's very vulnerable to windup. And windup is, or should I say integral windup, is where the value increases way too much and has no upper limit. In these ways, it can be more of a detriment than a benefit. But like I said, there are some cases in which the derivative component is less useful than that of the integral. And in the cases where integral is more useful, it's quite helpful. The integral component is calculated thus. If the error is less than the integral bound, then the total error equals the error plus total error, which essentially is an increment. Otherwise, we reset the total error back to 0. If the absolute value of the error is less than the integral bound, then the total error is simply incremented back to the value of 0. Otherwise, it's just reset back to 0 in simple terms. Then, if the absolute value of total error is larger than the maximum integral, the total error is multiplied by the value of maximum integral, as well as the sign of c state of the total error. If you're confused what sign of c is, it's right after this. So don't. Otherwise, the total value of error is simply assigned backwards. The sign of c method is a method that returns a positive or negative value depending on the sign of the number, the input x. So if x is larger than 0, then it's simply going to return 1 to 0. If x is smaller than 0, then it will return negative 1.0. Oh. And then it will just return x. Well, the input x that we were given in the first place. If it's 0, well, it will just give 0 and then return x. It's pretty straightforward stuff. Oh. Now all these three components together. Kp is the proportional coefficient, Kd is the derivative coefficient, and Ki is the integral coefficient. The value is used, this value, lateral motor power that we calculate by error times Kp, derivative times Kp, and total error times Ki is used to call the motion functions, the motion functions of the robot. The process of manual PID tuning is used to configure the coefficients. And the simplest way to do this is to have the user slowly increase the Kp coefficient first. And like I mentioned, the proportional component is by far the most important, which is why you want to make sure that value is as close to the target as possible. Kp is slowly increased first until there is a minimal oscillation or displacement from the destination. Then I said that there was a reason why I did PDI and not PID, even though the algorithm itself is most commonly called PID. This is why. Kd is slowly increased until the steady state error diminishes. This is because having the integral component this early on is bound to make the results go all over the place. And as a result, it's going to be much harder to tune the remaining derivative component, then it would be the other way around, which is why KD is always after P, but not after I. KD is slowly increased until the steady state error diminishes, and steady state error is essentially the robot going up to the destination and just kind of oscillating back and forth, like almost as if a pendulum. You don't want that. Then finally, Ki is increased until there's little to no oscillation or steady state error remaining. And well, if the resulting movement is one fast and fluid motion, the tuning can be considered successful. So let's move on to testing. In order to see the effect of these components firsthand, testing needed to be conducted on robots that are built simply and for the sole purpose of autonomous motion. Two VexIQ robots, so more specifically, were used. One of them was weighing 900 grams and the other weighed 1200 grams. Both used the same wheel size, 200 millimeters circumference, and also the same type of motors. The distance between the wheels was also made sure the same. I made sure to keep those constant so that it would be a fair trial. Each of these robots were given target distances of either 1 or 2 meters, and then the displacement from the destination was measured. Manual PID tuning was employed for all the 1 meter experiments and then repeated for the 2 meter experiments. This led me to two hypotheses. Hypothesis 1 was that the accuracy of the PID, application of the PID control loop, is affected by the distance traveled by the VexIQ drivetrain. This is because depending on the distance between the origin and the destination, the PID control loop algorithm will get less accurate the farther away the target is. And this can be due to many possible sources of error, which aren't even software related. Most of it is actually hardware related, such as veering in one direction, random hardware errors or sensor errors. Hypothesis 2 is provided that the technical configurations of the robots are similar to IQ motors, 4 wheels, each 200 millimeter circumference. The accuracy of the application of the PID control loop algorithm should be similar for the robots of different size and weight. If both robots are similar in the hardware used, as mentioned, motor type, drivetrain, wheel type, then the accuracy of the PID controller with similar parameters will also be consistent, regardless of the size and weight of the robot. Now moving on to results. As can be seen here, they all coalesced at 0.9, and this was a source of interest that I'll discuss later in the conclusion section. But this is just about, do you see this consistency here? Good, because that's about as far as it goes. Everything else that comes from here is not consistent whatsoever. So that's the 900 gram of KP gain, the very first one. It's for 1, 2, and then Then came the derivative gain, which, as I mentioned, is KP and KB together. So again, consistency here, still for now. For now it's still here, but not for long. The blue line denotes 1 meter, the second line denotes 2 meters. Then it's all 3 components put together, and the results here are, they're kind of consistent, but at the same time, it starts to go all over the place. But I think in the end, it did come out that this was the optimal. This was the optimal solution because it had either zero error. Yeah, it looks like there was zero error there. Then came the second robot, and the second robot started to get a bit more interesting for reasons I'll discuss later. The second robot started to veer in one direction a bit, and as a result, it became harder to take results, even though I made sure to try and harness with this. And the KP gain was a bit interesting. As you can see here, it's just kind of like a sine wave, except much more convoluted. However, it only started to actually get close to zero or be at zero all the way at the end, which was a big concern. In fact, what was even more concerning was the derivative gain, because whatever consistency there was, it's gone now because for instance, the 1 meter measurements seem to be going down while the 2 meter measurements seem to be going up. It doesn't make any sense. So does the integral. And you can argue that there's a bigger pattern here, but at the same time, it's still too dispersed and spaced out to make an effective conclusion of it. Then for the results of hypothesis 2. And yeah, there's no consistency in this. This time it's the comparison between 2 robots and not 2 distances. And as you can see, the whiter robot had a significantly easier time just stopping at that preferred distance. Then once you apply the KP but for the 2 meter test, you can see again that the 1200 gram robot just suffers. And I could not identify why this was the case, even though this one seemed to be getting closer, but the 1200 gram robot just kept going all over the place. Then once we put together the derivative component with 0.9 kp applied, this started to really go downhill, literally and figuratively.
Oh my god.
Yeah, it started to get very bad. And as you can see, by here, it's just gone off the deep end. And by that point, I was just thinking, what have I done wrong? But I tried it again, and I got the exact same results. So. But as I mentioned, the 1200 gram robot is suffering. It just suffers, seriously. And here it started to kind of hook up again, because towards the end, they started to get closer again, and I thought, oh, maybe they'll actually start to correlate, but unfortunately, my measurements ended there, so I couldn't test that in more depth. But again, the 1200 gram robot suffers a lot. Now, what didn't make sense is the integral, because the 1200 gram robot just took off. It just took off. It started to overshoot all over the place, and that's because of the integral component. We know why that happens. But the 900 gram robot did a fairly decent job of staying at the same destination, so to say. But yeah, the 1200 gram robot just sucks. It just sucks. And finally, the final test of 0.9 kd, 0.1 kd applied with the 2 meter test for both. Yeah, the 1200 gram robot it was not feeling good, so to say. But the 900 gram robot seemed to be doing okay. It could have been a lot better. So now that that's all the results done, let's go to the conclusions. In total, 120 trials were conducted, and that's 60 per robot. The KP, or proportional component results, were the most interesting, as they implied that the best value was 0.9 kT, which is normally not that high. I actually took a whole day off just to search up if anyone else had done 0.9 kP as their optimal value, and there are very little people who even got to 0.7. So this is very surprising. The proportional component was also the only component in which both robots had exactly the same results at first, namely the perfect stopping distance, because if you remember on the first 2 graphs, they were quite literally just stuck together. Another thing was that originally I had anticipated that the derivative component would be somewhat effective, but it didn't seem to help as much as I predicted, even though it seemed to be helping at first, but the results just went off a cliff from there on. The derivative, I think the derivative could have been too high, and that made robots stop faster than necessary, which of course increased the displacement from the destination. And finally, the integral component results were the exact opposite of the derivative ones, and this surprised me the most throughout this investigation. And this was originally expected to cause overshoot and not actually improve the results. As the values increased, it became apparent that the integral component served to improve the results and not to make them deteriorate. And I had never expected it. I think that while this could be because of an optimal KD value chosen in the previous trial, I still think that the integral value here, the integral component here, is quite large for helping the robot to become more accurate. Hypothesis 1 was supported to an extent, as the proportional component influenced the result very similarly, while the other two components had massive fluctuations for both robots. And as for hypothesis 2, it just wasn't supported whatsoever, as the higher weight of the 1200-gram robot made it noticeably harder to stop at the destination, regardless that they were using the same hardware, making for a huge rift in the results, as you saw between the KD and KI tests. Through this investigation, the PID control loop algorithm was used to find the optimal coefficients for each robot that would allow for precise stopping and smooth motion. And the fact that a single algorithm is capable of making robots move and stop smoothly, well, somewhat smoothly, in autonomous mode opens many new possibilities all across industry. So, the results show that the accuracy of the robot's performances in the autonomous mode with PID enabled decreased as distance increased. Also, the robots with similar technical characteristics behave differently if their size or weight was different. When programming robots for carrying loads, it might be more beneficial to program different PID coefficients depending on the situation, because 9 times out of 10, the situation is what makes the PID control algorithm different. There's not many situations in which there's coefficients that will work for all types of situations. The experiments have shown that while they yield different results for the trials with different coefficients, there are some instances, miraculous instances I might say, in which they match across distances and robot types. For the most part, however, the PID control loop algorithm coefficients cannot be unified effectively for the VexIQ robots and should hence be tuned manually to maximize efficiency. Which is why, hence, the coefficients can only be unified to a small extent, which is a shame. I hoped for much better. There were a number of flaws in these experiments. For example, the 1200-gram robot, as I mentioned, it had a hardware deficiency, making it veer to the left and negatively influence the results. And I think that was caused by a shortage of parts for both robots, forcing me to make sacrifices in build quality. Finally, it could be said that maybe 120 trials are still not conclusive enough to make a good conclusion or evaluation. Well, in any case, experiments could be repeated several more times to ensure the accuracy of the coefficients obtained. There are some further avenues for improvements. One way is to improve the experiment is to rebuild the 1200-gram robot from scratch so that it can move without any veer. Because in retrospect, the veer was horrendous. It would require a lot of work, and it wouldn't absolutely guarantee any improvements in the results. It may just be that the robot itself is broken, so to say, or maybe it's just a tire problem, and there's no way that can be fixed. Increasing the number of tests by either 50% or more can also be beneficial to improve their quality or quality. And well, finally, utilizing only one of these techniques may not make for a noticeable difference, but combining these two could have significant and positive effects on the accuracy of the results. Bibliography, acknowledgements, because yes, and appendix, way too huge in this presentation. If this presentation wasn't huge enough, don't ask for the appendix, please. And that's it. Thank you for listening.
Okay, let's have a Q&A. Let me first ask those on Zoom, if you have any questions, please type them into the text chat. Those here in the audience, any questions for Pavlo about his investigation? Yeah, you're lucky. Sure.
So on your graphs, right?
Yes.
You know how there was a lot of fluctuation. How many? Okay, can I first ask how many like trials per graph did you use?
Trials per graph. That depends. Per graph, there's usually, I think not even usually, there's always 20, but
20. Okay.
it's just separated by category. As I mentioned, that there's different distances and different robot types, which meant there were a total of 12 graphs.
Okay. So and my actual question is that for your fluctuation, did it always have that fluctuation for every single individual result, or was it the added like mean, like the average like data will have did only the average data have the fluctuation, or did every data have the same fluctuation?
I think the overwhelming amount of fluctuation was in the 1200 robot, and as a result, that influenced the average small.
No, like did every single individual result have fluctuation?
No,
Like, not just the average.
well, I'm not sure honestly. I don't think it was too harsh, but as the graph showed, it was big enough, and yeah, it was big enough to understand and see.
Like,
So yeah.
Other questions, audience here?
How do you look at the chat?
Nothing there. Yeah. One question. I was wondering if I suspect the reason why you got that 0.9 coefficient to be the optimal. This is my hypothesis. Is maybe the surface, possibly the surface that you were doing your tests on might have been
Attention please, all middle and high school
like
students.
high friction or very low friction, I don't know. But something, maybe like testing on carpet, for example,
You will start.
that might, like the surface could, and I suspect does, have an impact on those, on the optimal coefficients. If you're testing on, say, like a tiled surface like we have here versus a carpet, I'm sure that those, for optimal stopping, you have different coefficients. I'll just wait there, guys. We're almost done.
While that is a good source of concern, I did make sure to include all my results. Well, I made sure to have all my tests on Pavlo. And actually, let me show you right now.
I'll wait there, please. Wait there.
So yeah, more than 4. So it's not carpet. There's not there's literally no friction.
Yeah.
I even made sure it was parallel with the little creases or whatever. So
Interesting.
yeah, it's still a mystery why 0.9 is the key to it.
Okay. Okay.
Anyway, I guess that concludes everything.
Yeah, thank you. Thank you. Okay, one more round of applause for Pavlo. Thank you. Okay, thank you, everyone. Thank you. You coming now? Yes.
Okay, thank you.